Okay, the first task in data pre-processing we want to cover is missing values. And we're going to introduce some of the methods that address missing value issues. So we've seen in police shooting data, some they're empty cells or cells filled with NA, not available. Well, even though those cells are filled with NA, but I want to draw your attention that many times the meaning behind NA are different. So I provide a simple categorization of different situations. An empty data cell could mean the value for that data exists or not exist. When the value exists and available but is not recorded due to human error, or in some conventions, negative values are left empty, becomes not available. So this is one type of missing data. Another type, value does exist, but not available. For example, when I fill my applications for, I don't know, the citizenship form, they ask, what's your grandpa's birthday? Well, my grandpa obviously has a birthday, but how do I know when? I don't know my grandpa's birthday. Seriously. So the value exists, but they're not available at the time for me to enter that value. So that's a second semantics that a missing data could carry. In other cases, the value itself may not exist. For example, this value, absence of a value. I don't have a middle name, therefore my middle name box has to be blank. In other cases, it's simply not applicable. If you give me a form to measure tail length, I don't have a tail, therefore I cannot measure my length of the tail for you. So those at least 4 different semantics that the empty data cell could carry. However, in vast majority cases, what we saw is all of these are lumped under NA, not available. I mean, it's really unfortunate that when we record the data, those different things were not differentiated. Ideally, different semantics should be encoded as different values. NA not applicable, NA not available, to differentiate those. But yes, in reality, I really saw some of the biology data differentiate those two, because certain features certainly doesn't apply. An invertebrate doesn't have the spine, right? In majority of the other cases that I see, all the missing values being represented by one single label, that's problematic. So we know there's missing value, then how can we handle those? Easiest way is to simply ignore the observations that contains a missing value. This is not a very good solution. Well, actually, none of the solution is good. I mean, perfect. It's best not having missing data. When you have missing data, you find the best way that's available to you to fill the data. But none of the methods is actually ideal. So ignoring tuples certainly have issues. You cannot do that when the missing value is the class label that you are predicting, right? When doing classification, you cannot remove tuples if every tuple have some missing value. Then you're going to ignore all the tuples. You don't have any data to analyze. The second possible way is to fill in the missing value manually. This would be the ideal, probably the best solution. You go back and find the missing value and fill it in those blanks. However, you encounter major feasibility issues, how many human labors that you will need to perform that task. You can also replace empty cells with NA unknown, like R does that conveniently, and we already discussed the problem earlier in the earlier slides. Though we just simply mixed those. For example, height, your score. Somebody's score could have been 100, but others could be 50. Because they're missing, they all become NA, they become the same thing. So you hide lots of variations in your data by simply enter one value for all missing values. So that's also not ideal. Then there are a whole set of possible ways that you can do to fill in some values automatically. For example, you can fill in a global constant. This is exactly the same as this solution. We know that's not good. The attribute mean or median for that column. So if you have certain value missing, you can fill in that value with the mean or median of that attribute. This could also be mode if you have categorical values. Well, this can be a way to deal with it, but if you have lots of data missing, you have smaller number of data available. Using smaller number of available data to fill in larger number of missing data, you certainly have introduced a lot of biases into your data set by using this method, right? Another way is it's a little bit smarter is to compute the mean, median, or mode for all samples belonging to the same class. Let me add that. For categorical and numerical data, for categorical you can use mode. For numerical data, depending on whether the data is normally distributed, you can use mean or median as the value to replace the missing values. So in this example, if you're doing a classification task, you take one class and class by class you fill the missing value using the mean, median, or mode. Again, it's just the problem might be at smaller scale, but you still have the problem of introducing something artificial. You could also use machine learning or regression methods to predict the most probable value. Next, we're going to introduce linear regression. That's one way that you could use to fill in the most probable value. You could also use, later on, we're going to talk about a Bayesian network, use Bayesian inference or using decision trees to predict what could be the most probable values for a missing value. This may be the best, but is this problem-free? I would say not, because you basically reinforce the bias of the model on your data. So, as I said, nothing is ideal. The ideal solution is not to having missing data. So linear regression is one way that we could actually So now we're going to introduce the regression as one way to fill in missing values. We're going to actually talk about the most basic, simplest regression method, the simple linear regression. Regression does not have to be linear. Regression is a family of techniques that they are also non-linear regression. It doesn't have to be simple. Simple, by simple, we mean that we only going to study the relationship between two continuous variables. You could actually study relationships between multiple continuous variables. Those are called multi-regression. But we're going to use simple linear regression to illustrate the concept of regression, why it's suitable for a number of data cleaning tasks. So in this example, we have the independent variable height and a dependent variable weight. So we're going to use height to predict weight. Independent variable is also called predictor. Dependent variable is also called response. So our goal for linear regression is giving a set of observations. So we have a set of individuals whose weight and height values are known to us. We're trying to find the best line that fits the data. So we have y being weight, and this x is height. So we're using height to predict weight. If we look at this picture, I took it from Khan Academy, so acknowledge their contributions. So here we have set of data, we have height and weight, and those are the observations scatter plot, right? We plot this and we notice a very clear linear correlation there. So it's highly possible that we can fit a line there. And we're fitting this line so that with this line that we can have for this observation, we can actually start to see how we can predict. So we have observations 60 and 100. But if we have another observation at 55, we can draw up a line here and meet this our regression line, and we can predict the weight, right? For using this linear regression for this person with a height of 55 inches. Fitting such a line that, as you can tell, there's multiple lines we can fit. We can fit this line or this line or even this line. And we need a way to assess how well this line is, how well the line fits the data. The way we assess the goodness of this line is by computing the residual. So the residual is the difference between the real value, 100, and our predicted value. Our predicted value in this case is 150. So we have a residual of negative 50. If we have those positives and the negatives adding up together, we got 0, right? So it still doesn't tell us how well one line is compared to other. Therefore, we have to either use the absolute residual or the squared residual to measure the goodness of the line. We're going to sum up all those residuals. So look at the difference between each predicted value and the real value. So we have those, adding up the square value of those together, we get our least square regression. Okay. So coming back, so this summarizes what we just saw. So the goal of the prediction is to find B and A, right? Because this line is determined by its B, the slope, and the A, whatever this is, the intersection. Intercept, yeah. So this F is our predicted value, this Y is the true value. So our sum of square, the residual, would be this term, okay? So we want to find such a line that minimize this function. We want to find a line that make the residual total sum square of the residual the smallest. Then to assess how good the fit is, we use the coefficient of determination, which is R squared. R squared is defined as 1 minus the residual divided by the total. What is total? Residual we already discussed. It's this term. What's the total? The total is actually the true value, the sum square of true value, the difference between the true value and the mean value. Okay, so basically this R squared tell us how different our predicted line creates the residual as compared to if we just predicted the mean value. If we don't fit this line, instead we find the mean value here on height and just using the mean value as this line to predict. No, we're going to actually, using y. So we find the mean value along y-axis and using this line to predict, and see how much of the residual we're going to get. So we compare the goodness of this line to a goodness of maybe this line. Okay. So as we can tell, R will reach its largest value 1 when this residual is 0. So our prediction fits the true value perfectly. So there's no difference between every pair. We have a 0 here, we will have R squared to be 1, right? R squared could also be negative value, meaning that this is greater than this, meaning the difference that our prediction line is actually greater than the residual of using the mean. That would be the worst situation that you could possibly imagine. So R squared, for a simple linear regression, R squared is good enough. However, as later we're going to mention, this multilinear regression, where we can use multiple variables to predict one variable, x and the beta now are vectors. So there's multiple variables x, and for each there is a beta as weight for this x. In those cases, R squared won't be sufficient because we know adding more and more variables will naturally make the line a better prediction of the observed value. So here we introduced another variable p. P is the number of independent variables introduced into the model. So basically that's the number of x. So the more we have that, the greater R2 going to be. So therefore while they have come up with this adjusted R squared to take into the consideration of how many independent variables were introduced into the model. With this, as you can intuitively see, the greater the p-value, the smaller the R squared adjust going to be, to account for the fact that those added variables could actually just be accidental, add accidental powers to expand the dependent variable. But those are really details that we won't use this fact in this class the second time. I just want to draw your attention. And linear regression, it's to find the best linear regression, it's not just looking at the R squared or adjusted R squared. We also have to plot. So for the residuals that we have received, they ideally, if we actually finding a good model, a good line here, those residuals should be normally distributed. So one way that you definitely want to do when you perform regression is to check the residual plot. That is covered in this link and some other tips. If you are interested, you can look into that. So we have described the technique, the ideas behind simple linear regression is fitting a line and find the residuals. By evaluating the residuals, we know how good this line is. Once we have this line, we can predict the value given x, we can predict y, right? This linear regression can be used in a number of data preprocessing tasks. For example, missing value. We can use the predicted value to replace the NA, right? Data smoothing. Again, the original data may have noise, but once we have a good linear regression, we can use predicted values to replace the original data, which will make our resulting data really smooth, linear, right? It's very smooth. And data reduction, we could, in some more advanced mining techniques, we don't actually need to save all the original observations. We only need to save the functions and its parameters. I mean, what's the beta, what's the theta, and the outliers that might be in the data set. So for the subsequent mining, the input to those mechanisms going to be this formula and outliers. So it could also be used for data reduction. It can also be used for outlier detection. We can imagine, in this case, we don't have any outlier. They all seems to be fit on the, they all seem to be located at the both side of this line. We could, when we do linear regression, you can see visually, you might have a point here. So the dots that's far away from the regression line may be considered as an outlier. Okay, so this is, we're going to talk about missing values. Let me finish.